I'd like to thank the organisers for inviting me here to talk about Crossrail and speak in front of such an esteemed group of people within the construction industry, engineers, and I'd like to talk about Crossrail and give a case study in BIM. So how BIM, our BIM strategy, how we used it to increase the efficiency of Crossrail. We're going to first of all have a brief overview of Crossrail, just have a look at the complexity of Crossrail project, which was built under the City of London. Then we'll have a look at Crossrail BIM Basics, so how we approached BIM and our strategy. We'll have a look at how we created our common data environment, which was key to our BIM strategy, and then how we used the data that we collected. So Crossrail is a project that runs from east to west across London. In the central section, which runs right under the centre of London, there were 42 kilometres of tunnel drilled. This will eventually lead to 200 million more passenger journeys a year. And these stations are huge when compared to existing London Underground stations. So we're often finding with a lot of the stations, the Crossrail station would span 2 existing London Underground stations. There's going to be 24 trains per hour in the central section when it's finished, and it will increase London's transport capacity by 10%. In the design and construction, we've used 250,000 models, including 3D models. We've got 5 million documents kept in our document management system, 1 million assets and equipment across the project, 500 million GIS features, and GIS was a central part of our BIM strategy. And the total cost is now over £17 billion. So these are just a few quick glimpses at construction. That's the canopy at Paddington. These are the escalators going in at Bond Street. This is a huge app ceiling at Farringdon Station, which is a very complex concrete structure to install. And this is a typical platform. This is at Tottenham Court Road, but we were keeping all platforms consistent so that our passengers have a very consistent experience as they travel on Crossrail. The size of the stations resulted in huge pieces of equipment needed to be installed, and this was a very challenging thing to install them in very congested construction environments. Also, we had artwork across the Crossrail project. This was all privately funded, so over £2 million worth of privately funded artwork at many of the stations, if not all. And a whole new fleet of trains. So these are state-of-the-art trains with new software on board that had to deal with several different signalling systems. So across Crossrail, you've got the central area, then you've got east and west, you've also got the spur going down to Heathrow. Each of these has a different signalling system, and each of those signalling systems needs to be spoken to by the train. So these trains have been extremely challenging, are an ongoing challenge for Crossrail. So project complexity. The bill went through Parliament back in 2005 when we were given the go-ahead to start Crossrail. The budget was fixed here at 15.9 billion. As construction started and as the design developed, this increased to 17.8. But then, of course, the government came in and had a review of that and dropped it to 14.8. As the construction has continued and due now to complications, you may have heard that we're now delayed delivering Crossrail. The price is looking like going back up to 17.6 billion. Also, there's massive contractual complexity. So each of these contracts across Crossrail need to be able to use the information that other contracts produce. So we needed to be absolutely sure of the reliability of the information that we were asking for and that was being delivered, so that each contract could use the information that other contracts were providing, and they could know where to get it and rely on that information. So the construction complexity. This shows Liverpool Street Station. These are existing London Underground stations. That's the Circle line, the Central line and the Northern line. And then there's the Crossrail station in the middle of it. So as you can see, Crossrail spans 2 existing London Underground stations, and this is in the heart of the business district in London, with huge skyscrapers, deep piles, and a very challenging construction. This also shows a small video showing the interface with those different utilities and existing infrastructure. So you can see the existing line here. This is our TBM coming through here, and this is existing LU infrastructure. So these tunnels, as I say, are 42 kilometres long, 21 kilometres each, so there's 2 tunnels. And the distance between the tunnels, the existing tunnels there and the piling there was less than 1 metre each side. And when you're dealing with that length, the accuracy of the data that you need to programme those TBMs was again very challenging. So also the physical scale and complexity of the Crossrail project is replicated by the scale of our virtual world. And this is where we come into BIM. So not only do we have all the construction assets, the physical assets, we also have digital assets, and these are just as important. So we have various systems, various documents, drawings, relationships, and relationships is hugely important. Can you go from one bit of information to another bit of information seamlessly? So effectively, we were building 2 railways. This is Canary Wharf, which is built, and that's the digital replica. Also, we had to think about who we were giving our data to. So not only did we need the data that we were collecting to be reliable amongst our supply chain, but also we needed to think how we're going to deliver that data onto our stakeholders. So we've got Network Rail, RFL, which is Rail for London, London Underground, and London Underground at TCR. So how are we going to pass over all the information that we've collected about our assets so that they can realistically use them in whatever asset management system they have? And this was a lesson learned perhaps by Crossrail in that next time we would probably hand over our entire asset management system rather than have our own. We used Eclipse, and then the end user putting those into things like Maximo, just to save cost at the end of the project. So the BIM Basics. What we needed to do is have a defined end game for all our data. So this starts right at the beginning about what type of data you're going to collect, how you're going to collect it, all the individual attributes associated with that data. You need to know how to classify your assets and data structure. And this is all procurement critical. So right at the beginning, we wrote into contracts with our supply chain exactly the type of data that we needed from them. We prescribed where they were going to put it, how they were going to put it there, so that everyone could rely on that. And that brings us on to the common data environment, which I'll speak about shortly. That's our electronic document management system and our electronic CAD management system. And this had to be used by everyone. Again, this was contractual. And it was owned and managed by us. Also, we needed to leverage technology. And by that I mean we needed to use a single database that could relate to various types of software, if need be. Going back to what is BIM, I think everyone has a different idea of what BIM is. For Crossrail, for ourselves, it was managing data. The data environment, where data is being put, so the CDE again, data integrity, the reliability of data, is it consistent? Collaboration, can everyone access that one source of data? Also using technology to increase the power of that data, and thinking about the whole asset life cycle. So not just thinking about design, construction, but also thinking about how are the operators, how are the maintainers going to use this information. Which brought about new processes and new cultures of work for our supply chain. So again, we needed to engage the supply chain to make them understand why we were doing what we were doing. If necessary, we needed to train them in various software, various processes. And this was very important because it's very easy to come across resistance to BIM strategies and to general change. So it's very important to educate your supply chain if you want them to follow what you've contractually asked them to do. This graph just shows that, again, lots of people think BIM is 3D models, and in the concept and design stage, 3D models are very important, but the importance of them lessens, and the data collected against assets increases. So at the end of the project, it's really the data against those assets that is the most important thing. So creating our common data environment. This is a little reminder of the old world. So all different disciplines speaking to each other separately, keeping their information in silos, not really giving people stuff in real time. So you would receive stuff that was old often. So with a common data environment, we kept all our data in one single area and everyone would access that. Again, contractually, we made them access it, and all their information went in there in real time and could be accessed by everyone in real time. So 90% of our data was in 3 linked databases. GIS mapping, which was hugely important to Crossrail, effectively a Google Maps of the whole Crossrail project. But you could go into that map, you could go into a station such as Farringdon, you could go into a room in Farringdon, you could find the asset information associated with that room. That would then lead you to EB, which is where we kept all our documentation, our reports, contracts, health and safety documents, all the drawings that came out of our CAD. And then we kept all of our CAD in ProjectWise and nowhere else. So anyone working on the Crossrail project needed to work within ProjectWise in real time, so that anyone changing a model and issuing that model and sharing it for others to see, people would see it instantly. And all these databases are linked, so that they have relationships between them, and you can go from a model in the ProjectWise and instantly know where to find information about that in EB. So this resulted in effectively our digital end state here. So this is, if we look at an asset breakdown, this is a facility, in this case a station, and in this case Farringdon Station. If we go further down to a primary functional unit, which is an escalator, from that escalator, that information about that will be held in the GIS, it will be held in 3D models, it will be held in as-built drawings, which are PDFs. You'll have health and safety records about that, maintenance concepts, test certificates, etc. And if you break that down even further to handrails, for instance, or stairs, or motors, each of these will have an operations and maintenance manual associated with it. So what we've created is you could start with the GIS, your Google map of Crossrail, and very quickly drill down into how to maintain a handrail on an escalator at Farringdon Station. So how did we use this data in construction? We again prescribed how people needed to deliver their 3D data. Everything on Crossrail was contractually in 3D, and drawings were cut from that 3D data. So everyone who was working within ProjectWise would see each other's 3D data in real time. And that's all about space management. So it's using 3D models to coordinate, and it was very important for us to be specific about the file format. So everyone working within ProjectWise, contractually again, we made them work in a specific file format, specific versions of a specific file format, so that every person's 3D model would automatically fit within everyone else's 3D model, all geospatially correct. And what we learnt as well is that we needed to insist on regular model updates. So some people would be working away on their model and might not share it for a year and a half, and other people are working on old data. So to have, again, written into contracts, which is something we didn't do, but we've learnt from that, is to insist on regular model updates. and also smart construction. So here we have a train going through one of the tunnels. Obviously, lots of equipment needs to be installed in these tunnels, walkways, CMS, fire mains. A huge amount of manual work would be required to drill the holes necessary for all this equipment. So each of the tunnels was scanned. This scanned data was then fed into a digital format. All the locations of all the drilled holes were then inputted, and this machine rolled along and drilled the holes exactly where they needed to be, which made the job obviously extremely efficient, accurate, and far, far quicker. We also insisted on project dashboards, which are often forgotten on projects, so that there is great visibility across the project of what other projects are doing, and also visibility up and down the supply chain. So there would be weekly, monthly dashboards showing the state of construction across each project, and also Crossrail itself produced these. So using data for asset management, we formulated an asset information management plan, which again was instructed to contracts, which they had to follow contractually. And this would define our overall approach to asset management, and it would list key supporting documents so that people knew what we expected an asset to be. So for example, I could call this a glass, someone else could call it a container, someone could call it a cup. I could say it's half full, you might say it's half empty, I don't know, but in Crossrail we had to tell people exactly what we expected an asset to be. So we would specify in AD4's asset data dictionaries what each asset was, what type of attributes to collect against it, so that everyone was clear across contracts and across disciplines what assets we expected to collect. And again, this was written into our contract clauses. So these are the asset data dictionaries, and they define the types of assets of interest to us, and this covered every single asset that could be installed across the Crossrail project, from pumps to walls. And we would hand over to our contractors spreadsheets which covered all the attributes that we wanted to be collected against every single type of asset. And those spreadsheets would be consistent across the project, and they'd be fed back to us, and then we would then input into our asset information management system, so that we can have reliable and consistent information across the project. So handing over into operations and maintenance. So we've talked about our common data environment. Everyone is feeding into this. All individual pieces of information lie in here. But we have different clients and we have different stakeholders, each requiring different types of information. So for instance, London Underground would require certain information that we would be able to take from our common data environment to hand over to them. RFL might require different information. It might be overlapping, but we can pick and choose from the common data environment because everything in there is consistent, and we're not having to go to various areas to find the information that we need. So, lessons that we learnt. Firstly, we learned that the best innovators in BIM were actually the best performers. So that's a very encouraging, practically, for the benefits of BIM. And we were finding contracts that were willing to engage with us and work towards a BIM solution actually performed better as a contract. So things we found were, in terms of our asset collection, we needed to define assets, as I talked about in the asset data dictionaries, very, very clearly, because lack of consistency, we found out very early on, causes trouble. We've also found that contractors release asset data as late as they can. They're busy building the station, and collecting data about what they've built is not necessarily their priority, but it needs, again, to be written into the contracts so that they can understand the benefits of releasing that data. So for processes like maintenance and operation, it's not just about building the stations. These stations will be around for 100 years, and it's far more important the data that we hand over at the end of design and construction. Also, again, maintainers need some asset data early for training, especially on projects like this with new trains and new software. So next time, we'll create and agree an asset data dictionary even earlier. You may have heard that Crossrail 2 is happening, which will be going from north to south of London, and that's what they're doing. They're building a complex asset data dictionary early. And we need to collect that asset data progressively, not wait till the very end and then try to collect it. Collect it as early as possible. And as I mentioned earlier, we'd hand over our asset information systems in their entirety, not just the data, so that it was easily brought in by our clients. The general BIM lessons learned. So again, data is the most valuable resource on our project, and it's owned by us. So it's in a common data environment. We know what's there. We can look at it any time. And everyone knows that we can, and everyone knows that other people can look at it any time. And it's very difficult to hide behind incorrect data or hold it somewhere that other people can't find it. We need to establish our requirements very early on, which goes again along with what information you need to collect about your assets. Structure the data with the end use in mind. So there's no point collecting all this data and then handing over an enormous great container full of bits of data that have no relationship to each other to a maintainer who can make no use of it. So if you know that this data is going to end up with an operations and maintenance team, then you need to be asking those and thinking about how they're going to use it and what's useful for them right at the very beginning. You need a good and clear asset breakdown structure and classification so that everybody understands it and agrees with it and complies with it and sees the benefit of it. And relational databases, so databases that speak to each other so that you can go to one to find information about the other and then from there go to the other. It's very important. And to become data-centric, which is the common data environment. Beware of data interoperability. So if you've decided that it is okay for people to use different software, for instance, High Speed 2, a rail project in England at the moment, they're allowing people to use their own software, but they have to be mindful that the data they collect will be able to be used by everyone else. Crossrail chose to prescribe exactly what software people used to get rid of that problem. Beware of being led by IT and software. So IT will always tell you we can't do that, or we can only do that, or we don't like that. So you need to decide what your requirements are at the beginning, and IT need to support that. And of course, people don't like change. The world is changing now, and BIM is becoming more and more important, and people are understanding the benefits of it. But even so, especially as you go further down the supply chain to smaller companies, manufacturing companies, they've worked a certain way for a very long time, and it's very difficult and costly for them to adopt BIM sometimes. So it's up to you as a client to instruct them and to give them the support that they need. So finally, all of the information I've talked about can be found on that website. I don't know if these presentations are available, but I'm happy for you to take this presentation away. And Crossrail in numbers, just to finish off. So 17.8 billion cost in the end. Over 4 million documents in EB, 468 assets that are being defined so far against the ones that have been installed. Almost 500,000 drawings so far, all the CDE users and the construction contracts, and it would have all been much harder without BIM. So the very last slide, this is, I don't know whether any of you have heard of Ray Kurzweil, who works for Google as an engineer there, and he he has theories which he calls the singularity. And this is all to do with the rate of change of computing power. So at the moment, computing power is progressing more each hour than it did in its first 90 years. So as we see here, the graph of computer power, and this is calculated by calculations per second that you can buy for $1,000. So back in the 1900s, you wouldn't buy very many calculations for $1,000. As we head up into the current age now, in 2015, the amount of calculations a computer could do for $1,000 surpassed the brain power of a mouse. That didn't mean it was cleverer than a mouse, it just means it could calculate more things than a mouse's brain could. In 2023, if the current trend continues, it will be more calculations than a human brain. And in 2045, Ray Kurzweil predicts that it will surpass the equivalent of all human brains on the planet. So in the construction industry, we need to be mindful of this and realise that technology is something that we can embrace and something that can really change the lives of not only us who use it as engineers and designers, but also the people who we're building for. So thank you very much. It was all for her. It was her. It's called the Elizabeth Line. Thank you very much.